I think you can start.
Just a minute. Am I right to go? Is that
Yes,
working?
go ahead, start.
Yes, I see. Okay, thank you. All right. So we'll come back to the beginning. Thank you. Thank you very much, Peter. Are we right to go? Okay. It's a great honour to be a recipient of the award. I'm very humbled by that, and it's great to have that award from a wide group of people I've interacted with in various ways, closely and more remotely over many years. I had the pleasure of meeting Richard Pike himself back in the early 2000s. I think it was at a meeting in Japan in 2001. And before then, he contributed to our work somewhat, because encouraging us to share our elevation modelling work from the early times that we were involved. Because in the earliest days, we were right at the beginning of elevation modelling, when computers were just getting under the road. Anyway, so this one. Have you got? Is that okay? That one? Hold on. That's better. Here's the contents for the talk. I'll talk a little bit about mesoscale and toposcale context, because in fact my work started from the climatic domain rather than the elevation and topographic domain, and they somewhat emerge after a while. So I'll say a little bit about surface climate and its topographic dependence, and then moving over to our experiences with elevation modelling and looking at some of the more important features along the way, which are still relevant to the modern day, I believe. And that will, of course, talk about ANUDEM and its locally adaptive multi-grid process with automatic range enforcement from a variety of important data sources, streams, lakes, contours, and cliffs. I'll then talk a little bit about recent applications to dense, noisy elevation datasets, which of course is which is the current domain. And if I have time, I'll say a little bit about specific catchment area and how you should be able to calculate it a bit better, and end with a few take-homes as a conclusion. Okay, so so this sort of scaled depiction is very common, I guess, but the mesoscale is the one which is where the climatic domain climate elements are mostly active, and it's where elevation-driven lapse rates control monthly climate, I should say, and surface morphology, the so-called toposcale, controls catchment hydrology, slope and aspect effects, topographic shading, and so on, and some of the finer scale aspects of climate as well. So to bring this to a little bit of pictorial life, here's a picture on the left of a very...
Can I just jump in there?
Yes.
We're not seeing the slide you're talking about. We're still seeing the kind of the editing view of the thing rather than the presentation view.
Ah, okay. I put it on to full screen.
You may want to put it to full screen.
And it may be that Zoom is sharing the wrong screen.
Right. Oh, okay. Wait a minute. What can you see now?
Maybe you want to start the presentation, since now it's in editing mode.
Yeah, I think click that button.
Yeah, that's what I thought I did, but maybe I didn't.
Yeah, so what is that? Nothing's changed. So we're still seeing the outline and the kind of edit view.
I can see slide 4.
I can see slide 4 as well.
Yeah, the same for me. Slide 4.
But the point is, it's not full screen. You may want to change the full screen or just go ahead like this. But in this case, you have to click in each slide on the left where you want to go ahead.
This is not working, this view, I take it?
It's working okay.
Shall I proceed with this?
Yeah, why not?
Okay. You can see the slides. You've got two slides of an elevation model overlaid by temperature and a picture of hills in Wyoming. Can you see that?
Yeah, we can see that. Yes.
Yes.
Okay. All right, we'll proceed. Perhaps I should wait for the slides to catch up with my voice. It's part of it. Anyway, so on the left, you can see a cardinal example of elevation-driven surface process, which is annual mean temperature, in this case, over part of northeast Queensland, where the dependence is virtually linear. As most people are aware, that the temperature declines almost virtually linear with about 6 or 7 degrees per 1,000 metre rise. And given that, you can describe quite accurately the surface distribution of temperatures across vast areas using quite limited data points. And that's where I started in the game of surface modelling climate and then into elevation modelling. Because if you have elevation dependent climate, temperature, rainfall and so on, and I'll show you rainfall as the next one. Well, before I go on to that, I wanted to say that the toposcale on the right shows you that at times dramatic impact of slope and aspect on surface processes. This is a mid-latitude location in Wyoming in the United States, of all places, showing round off grassland on the western side, I think, and forests and ice and snow on the other side, which is quite a dramatic shift. And these are the sort of changes which we potentially talk about with climate change coming, yet here they are happening from one side of the hill to the other. So, but in a very systematic fashion. So when we talk about dynamics of change over space and time, with these sorts of things happening, it's good to be able to recognize these things and take these into account into the overall dynamics of these systems. And these, of course, is tied up intimately in the climatic domain with slope and aspect. So the underpinning model I used for describing climate was a thin plate smoothing spline model, which can be described fairly simply in mathematical terms as a trivariate function of x latitude, longitude, and a suitably scaled elevation. And the solution is to minimize a combination of the residual from the data plus a measure of surface roughness. And this technique was developed in the early 1980s by Grace Waber and colleagues. And I was fortunate enough to be around at the time when that happened, with a need to interpolate climate, and implemented these things effectively. And that's where my climate modelling began, spatial climate modelling began. And with those techniques, you can turn the mess of data points, of rainfall data points across Australia, measuring rainfall, into the rather glorious picture of rainfall for, I think, January, for mean rainfall for January from those data points using these thin plate spline methods. And if you look carefully, you can see the effect of the scarp, the Great Dividing Range on the eastern side.
Mike, you need to advance your slides. We're still seeing slide 4.
Oh, really? Oh,
yes.
Oh, okay. Just a minute. Maybe I'm using the wrong button. What can you see now? Still.
The thing is, we're looking at a different screen to the one you're looking at, Mike.
I see.
I'll get out of it. We see slide number 4.
That's it.
That's fine.
Okay, the next one, I think you wanted us to see the maps.
Okay, can you see this one now? I've talked to this one already. This is the thin plate smoothing spline model. Can you see that?
Yes.
Yep.
You can.
I think Michael shared the application and not the screen, and that's why we are not seeing.
I think you can try F5 to do full screen. F5.
There we go.
No, Mike, just a quick stupid question. What did you share? Did you share your screen or did you share PowerPoint?
Well, it wasn't quite the same question, and I'm a novice in these things, so I went into Square Sheen. I expected to see something to click on. In fact, I got a question which I think I wanted to share, and so I clicked on that.
Okay. Maybe we'll leave it like that, and you just remember that now we see your slide number 5 in your PowerPoint edit mode, and then maybe you go ahead if you want to talk now about number. Now we see your slide number 1.
Yeah, look, I'll move on to slide number 5. Can you see that?
Yeah,
Perfect. That's the way
no more changes. We'll proceed. I wanted you to see this equation, if ever so briefly. Here is the thin plate smoothing spline model. Okay, and here is the maps of rainfall depending on interpolated rainfall depending on elevation. And to do that, we need. Okay. First, I wanted to show you that the rainfall dependence on elevation is not as simple as temperature. In fact, it's a spatially varying dependence. Whereas if you look at this picture of manual mean rainfall over the same place where we had temperature, then we have the highest rainfalls at the highest places, but the lowest rainfalls are not the lowest places over on the coast on the east, but they're over inland. So they're varying trends. And one of the nice things about these spline models divine appropriate dependencies, relative dependencies of elevation on climate, and the function on the top right hand corner of the slide shows you the dependence, the effect of varying the relative scaling of elevation with respect to horizontal coordinates, and it shows you that in fact the dependence of rainfall in spatial terms is 100 times more sensitive than it is to the horizontal. So that's that's a lot. That's a very much greater dependence. So in fact, elevation is so much more important than the horizontal coordinates in tying down the dependence of spatial patterns of rainfall. In fact, that mirrors the relative scaling of dynamics in the atmosphere, and that mirrors the relative scalings of the grid boxes in the global climate models precisely, about a factor of 100 to a 1 between the horizontal and the vertical. So these splines rather are showing that they're getting in touch with the underlying processes of controlling the surface processes in the atmosphere above the landscape. Well, that's very good, and that's what I wanted to say, that these climate models are good, and of course a lot of my life has been spent pursuing these climate models to greater degree of precision and flexibility in various ways. But of course, to make them come to life, we need an underpinning elevation model. There's no good having dependence of climate on elevation if you can't have elevation. And back in the late 70s, we didn't have any elevation models anywhere. The first ones when the very first coarse one was developed by the Bureau of Mineral Resources in Australia and in the late 70s. But with major, even though it was a useful first pass, but it had major drawbacks in terms of no range conductivity and major errors and various things. So that led us to support our climate in the initial circumstances to develop a series of ever refined versions of elevation models for the country. The very first one, which we released public, was in 1991, a range force elevation model using the ANUDEM procedure at a scale of 40th of a degree, or about 2.5 kilometers, which is enough to describe climate pretty well, in fact. But that's about that time when elevation modeling was really taking off, as saying, to show that it wasn't just climate where it was very useful. It was extremely useful for modeling hydrological processes, and that's why it drove the development of ANUDEM to better support these processes. So I want to describe a couple of key points about the ANUDEM model, and I think, since we've had a bit of a rough start, I'd like to have an idea how much time do I have left? Can you tell me that?
You can go for about 15 more minutes. We'll take a little bit out of lunch.
All right. Okay. All right. Thanks for that. Okay. All right. So, so the underpinning spatial model for elevation is a two-dimensional bivariate function model. It looks very similar to the spline model I showed for climate, but it's now solved as a direct gridding function in discrete terms, rather in a finite difference, multi-grid finite difference interpolation model algorithm, which mimics in broad terms, the thin plate smoothing splines we've applied to climate, but solved in a direct gridding approach to the landscape. So this underpinning direct gridding approach was actually developed by Ian Briggs in 1974, but I took that was the inspiration for the development of further development of ANUDEM. In its first application, once setting up the method in a more elegant form, as you can see here, in a multi-grid way, was applied not to the land surface, but to the bathymetry of the Gulf of Carpentaria in 1983. But we kept going with that and moved on to, before that. And so I want to give you an idea of what a multi-grid interpolation, how that works in pictorial terms, because solving this thin plate spline function across space is a highly ill-conditioned process if there's not much data. The underpinning biharmonic equation is highly ill-conditioned. So the way around that is to have a simple multi-grid or nested approach where you start with a very coarse grid, as indicated by the top left-hand corner shows you the source data, which in this case are the red contour lines, and a 5x5 grid approximately sampling the grid cells which happen to have data in them. There's a bit of a shift there, but so they're not quite where they should be, but never mind. The ones which are colored are the grid cells which have data points in them, and they are assigned the average of the elevation points in the grid cells. So at the very coarsest resolution, you've almost got complete coverage by averages of the data points. This gives you the broad scale pattern, the initial broad scale patterns, which are so hard to put into place from a large scale perspective from the biharmonic equation without data. And so the process is then to steadily refine that by steadily halving the grid spacing one step after another. And so you can see that the top tier shows the sampling being refined steadily to the finest scale on the right hand side, and underneath you see the corresponding contouring of the fitted grid at these various scales, and you can see that as we get to the right hand side, we've recovered essentially the original contour lines, but along the way we've taken along, or we've interpolated along the way all the intervening structure in a very stable manner. So, and one of the things to note about that is in the earliest coarse grid resolution, there are no sinks, and possibly one or two sinks in the right hand side. So. What are the features of what are the principal features of the ANUDEM program are to build on that basic finite difference interpolation method to add critical locally adaptive modifications to this to respect the natural conditions applied by surface drainage, streamlines, lakes and ridges and cliffs, and we'll move on to show what they look like, because this led to the construction of the ANUDEM process, which Peter has talked about as well. Shows you the basic workflow through the process, taking in input data. And the one I want to point out is the left-hand red arrow going and the circle going upwards from the results back to the data. That's where we spent a lot of our time refining surface data in the good old days, or the bad old days, when our surface data were rather more limited than they are now. We had to attend to the errors in the data in various ways, and that spent required a lot of elbow grease from my collaborators as well as myself. That was a critical part of the whole process. So if I move on to show it, so the core innovation from the method was automatic drainage enforcement. And so this is a couple of pictures from the 1989 paper, and shows you on the left hand side the first at first glance nicely interpolated surface from a very few elevation points. You can see that the data points are there on the screen. There's a couple of hill points and a few points here and there, and a couple of lower points here and there. And the point in the middle is a sink, which has which is a spurious sink, and we want to clear it in a sensible fashion. And my initial investigations was how to do that was, if you like, sink basis, or where should we go? And then I realized that where the possible places to go are limited. They are limited to just the saddle points in the drainage divide around each sink. So you don't have to search the whole grid to find where you might exit. You don't have to steadily fill this hole till you find a saddle point. The saddle points are defined locally on their own terms. And so the process of drainage enforcement is to find each sink in the grid, then go through every saddle point, and for each saddle point, this one in particular, you can flow down to a sink on each side or a drainage line or whatever. And in that process, when you come down to a sink, the sinks, there's a data array associated for each sink, which it records essentially the lowest sink, lowest saddle draining that flows by a course line into that sink. So in this case, the lowest saddle is point D, and so the program simply takes the two course lines, one going each side of the saddle point, and turns it into a drainage line, which then clears the landscape in between. And there are two important things to note about this. This overcomes, it removes the depression not by filling the hole, which is what a lot of grid-based methods still do, but it modifies the whole landscape. And in the process, not only does it clear the sink, it also modifies greatly the shape and the slope and aspect relations about the landscape around the drainage line. So it's not just clearing the sink; it's actually significantly enhancing the structure, the overall topographic structure, topo-scale structure of the grid. All the way around that spurious sink. And the other point I want to make is that here's another sink over here down the bottom, which if that was cleared, what I wanted to say was that there's a natural ordering in how the sinks are cleared. And so the natural ordering is to clear the lowest elevation sinks first. And they're associated with the largest drainage lines, so the most securely defined drainage parts of the landscape. And then if they're done first, then the later sinks are then directed towards sensible drainage lines, which link into those lower clearances. So here's the case in point is here, the sink here, S3, I think. If that was cleared before S1 was cleared, it would drain to S4, which would give a drainage line going from S3 to S4, rather than joining as it hasn't done. It's in fact joined onto the drainage line going from S4 to S1 in a sensible fashion. So the process is actually is mimicking the drainage, the landforming processes of fluvial landscapes rather well. And this is verified by comparing real streamlines on the right-hand side as defined from this same minimal set of scattered points. The main drainage lines, the drainage enforced lines inferred just from these few 120 points or so in this landscape have matched pretty well the principal named streams of this, as shown on the right-hand side, including the dendritic structure going on the main stream down here on the deep creek. So these sorts of things illustrate that this drainage enforcement process is quite a powerful process and quite a robust process. And one of the things to think about is why is it so powerful? And one of the reasons it's so powerful is because when you think about it, slope and aspect are differential quantities. Slope and aspect are what defines drainage structure, but they're differential quantities, and they depend quite critically on surface elevation. So small changes in elevation can make big, as we know, big changes in slope and aspect structure. Conversely, so losing control of elevation heights makes a mess of surface slope and aspect structure. On the other hand, if you control slope and aspect structure, then you have a very strong control, at least on the relative heights of your landscape, and that's underpinned the strength of the ANUDEM modelling process. Enough on that, I guess. We've applied those. We then applied ANUDEM to a range of streamlines, which they don't just go into simple genetic processes, but have major distributory structures and also braided structures. So I won't dwell on that to say that we were able to cope with all that. And all these things were needed along the way, particularly in our elevation modelling for Australia, where Australia has major braided systems and also some major anabranching systems, as indicated in the top right-hand corner. So I want to talk now about another aspect of fluvial structure, and the other underpinnings of, or the other plank of ANUDEM's features is its success in modelling or gridding contour lines and streamlines and lakes. And here on the left, in this slide, we should see a rather sparse source contour data set from northern Canada, the glacially scoured landscape, which is fairly low relief with many remaining lakes. Canada has the biggest population of lakes there is in the world, I believe, and the process of ANUDEM was enhanced by first by having a stable interpolation process, but also to recognise from the contour lines, the corners of the contour lines, the points of maximum curvature, whether they're convex or concave, correspond to streamlines which can be and ridge lines, which can be defined automatically from these contour data sets. And so on the right-hand slide, you can see how the ANUDEM program has divined automatically course lines coming from the corners, like the green lines here are divined course lines coming from these contour lines down to the stream down here. And conversely, if you look up on the top here, you can see the inverse process of ridge lines divined from contour lines going uphill to a high point. There aren't so many in this landscape because ridge lines are not so, because it's fairly flat and there aren't that many ridge lines, but they do exist. And so this has transferred some of the detailed structure inherent in the contour lines across the landscape between contour lines and down to streamlines. That's one good thing. The other good thing is to take account of the structure, the drainage structure implied by the surface lakes and streamlines in this landscape, because they're a major structure. And the other thing that which ANUDEM now does, or since the mid-2006 or so, was to incorporate all the conditions that these imply. These imply, for example, that there's a contour line around every lake, and that's a constant height, which can be estimated from the elevations reading process without knowing what it is. But moreover, every streamline that flows from lake to lake and lake to and from lake and down to stream to other streams, all those things need to be connected in a sensible fashion. If you take account of all those connections properly, then again you have very strong control on the structure of the landscape. This took about 5 years to fine tune, but by the end of it, it's worked remarkably well, as this slide rather indicates. And so it looks rather good in the local scale, but it needs to be applied into the broad scale. And here is examples of both. Here's the larger view of a part of northern Canada, showing how it's worked pretty well with just these relatively sparse contour lines and streamlines and lakes, which is essentially sink free. On the right-hand side, a scene from Australia, in the ACT, local Australian region, from 25,000 scale contours, and again with almost no sinks. So if you do the job, if your data are good quality contour line data, and there are no major man-made intervening features, which of course there can be, then it can do a pretty good job at getting these landscapes well tied down in an efficient way. And the searching process associated with sinks and saddles is a key part of that process to do that in a finite time. All right, so we've gone on to model cliff lines, and I won't say much about that, except that they exist across most countries, including Australia, and they can be also digitized, or I should say rasterized as indicated over there. And the process is robust and is able to cope with minor inaccuracies, spatial inaccuracies in streamlines flowing not quite inside cliff lines, as indicated over the left-hand side. That can be, they are gently perturbed when they need to be into something which makes sense in grid terms over here. So the streamline is located firmly inside the neighbouring cliffs rather than one side to the right or left, and makes good sense of the landscape. All these conditions are locally adaptive additions to that underlying finite difference interpolation method, which affords all these additions, which have become rather manifold by now, and but in a very stable fashion and in a finite time. I think I'll skip over that one because we can do. I think we're running out of time, and I want to talk about more recent applications to high density data, which of course is now pretty much the dominant process. Although I noticed that there's a talk later on today by Bartolomé Chipoa talking about comparing contour-based elevation models and LiDAR-based methods models, and it can be the case that the rather somewhat smoother and well coordinated structures obtained from contour data can be superior, particularly for some of the finer scale terrain parameters, than what can be divined from some of the LiDAR-based models. But I want to show here a couple of shots from our work with on the 1 second SRTM work we did with John Gallant and his team back about 2011 or so and before, and shows you that the smoothing the process that the underlying interpolation algorithm has is able to cope with the ups and downs of the SRTM data, as indicated by the profile on the left-hand slide, left-hand feeder. Here's a profile here, profile line here, and here's the actual vertical profile showing you the data, the spiky bits, and the fitted grid model as going through all the noise there. On the right-hand side, we applied range enforcement to this SRTM data to try and enforce sensible drainage structure across the whole landscape. And that was a mixed success for two reasons. One was that before that, I want to say as well that ANUDEM can be applied to grid data, and in fact, the later editions of ANUDEM can take grids elevation grids as inputs, not just contour line, not just selected points, not just small sets of data, but large, ginormous sets of data as per SRTM data and other sets, other data sets. But this opens a whole an interesting range of issues to do with sensibly determining drainage structure, in particular in such DNs, whether they've been reinterpolated by ANUDEM or other means, and that has led to the ongoing issues of trying to remove spurious depressions in these landscapes, and this has led to an important distinction, if you like, for me, between sinks which are due to local errors in data and sinks which are due to real structures in the landscape. And this is sort of borne out here in this picture on the right-hand side, shows that in the right-hand side we have enough streamline data to sort out the landscape without any remaining sinks, which are the black dots. But in the top left-hand corner, we have many remaining sinks in that landscape. So the process of removing these things is still a major challenge for processing, because if you remove these sinks by either by breaching or by single cell lines, you don't pick up on broader scale structure, which maybe you should do. On the other hand, just filling local sinks can lead to unsatisfactory structure of the landscape. So one thing I wanted to pick up on was a possible way forward in such things, which I have not actually explored yet, but an indication that the multi-grid process of interpolation which underpins ANUDEM may have a role to play, potentially. And an illustrator how it has played a role is in terms of successfully applying range enforcement across different neighbouring tiles to dense data, such as the SRTM data. On the left-hand side, we have an initial go at our range enforcement of 2 neighbouring tiles, where I applied the then existing stream initialization process inside ANUDEM, which took note of the elevations along the streamline as they were. But the trouble with SRTM data is that there are errors, and some of them there were some low points somewhere in the data set which drove this streamline much too low than it should be. And so when it came to the edge of the tile, to the next one, it was nothing where it should have been to the next one. So this was actually fairly easily overcame by not using the elevations of the existing data at that final resolution, but to use the heights of the preceding coarser resolution of the iterative multi-grid process of ANUDEM. And so when that happened, all of a sudden these 2 streamlines and the heights around them lined up essentially perfectly without being required any essential stitching between the 2. These 2 neighbouring tiles were gridded totally independently, and yet they're matching up and they drain structure remarkably well, as the shaded relief plot shows. So I think there's ground for hope for doing these things rather better by taking account of using a rather hierarchical scale approach to things, but that is yet to be realised. I was going to say something about specific catchment area, I will, and that is that John and others have said much about this in recent times. But the thing I wanted to just point out is that there's a very easy process to understand that the divergence of the vector representation of specific catchment area is 1 as a density of area, and this can be readily seen by this picture on the right-hand side, which shows that if you integrate specific catchment area around any contour, any area bounded by contour lines above and flow lines left and right, the integral along this way gives you the total area above that contour line. The integrals along these lines give you nothing because they're orthogonal to the integration. Then the integral that way gives you the negative of the area above, and so the net integration around every such element is just the area of A of the enclosed area, and that says that the circulating integral around every such patch is the area itself. And if you then let that area element decline to reduce to limit to a 0 area, you get the definition of divergence, which is it's 1. And so it immediately follows from that equation that the equation the divergence in orthogonal contour coordinates using flow lines and contour lines, you get this equation in terms of along the flow lines, which translates directly into the equation developed by John Gallant and myself back in 2011. So what are the issues with the vector field interpretation of specific catchment area? Well, there are no simple shortcuts to its calculation. It's not a potential field in general, although it can look like that around peaks initially. But I believe that the best way around one of the good ways around, I should say the best way to represent it is to represent it as integrals around grid cell boundaries. These are well defined and could overcome the singularities which are often abound with specific catchment area, which goes to near infinity along streamlines. So, among other things. Well, I've been kicking around this idea for about 30 years now. We haven't got there yet, so so that's still to be done. And I talk about it with my collaborator John Gallant from time to time. So we haven't solved everything yet. So so I've got to the conclusion, hopefully in a finite time. So just a few take-homes, if you like. A process-based system modeling can lead to enduring models, and I guess I'd say that ANUDEM has done that by essentially aligning its modeling with the essential landforming processes of the landscape. To do that, along the way, you need appropriate mathematics, and that underpins not just ANUDEM, but also the climate models of which we talked about. But along the way as well, topographic scale, and particularly hierarchies of scale, are important in getting your models, getting the right dependencies on the variables, and getting sensible modeling outcomes from sometimes very challenging data sets and challenging equations to solve. No model is perfect. Of course, ANUDEM has continued to evolve over the years. And as part of that process, details matter. Details, we spent most of our life examining these details and acting on them. Outliers, remaining sinks, and other shortcomings, they all matter. And they come from the user testing and experience, whether from our immediate collaborators and from people far afield around the world who've come back with shortcomings one way or another. And I'm indebted to not just my immediate colleagues, but also the constructive feedback from many users around the world to make good progress. Some of those people are here today, I believe. And that's the end of my talk.